We're going to start by looking at the E1 elimination. E1 stands for elimination unimolecular, and the unimolecular part tells us there's one molecule in the rate determining step. So this is the same as SN1. So let's take a look at a simple E1 elimination. And I'm going to start with a tertiary iodide. And the rate determining step is identical to the SN1. What we do is we lose a leaving group and we form a carbocation. Right, from there, now what will happen is we need to do the elimination part. And this is where we use something as a base, whatever reagent might be present that has a lone pair, and then find a proton next to the carbocation. The base will grab that proton. Those electrons will then come down to form a pi bond. So we get our alkene plus our protonated base. So because this first step is the rate determining step, the rate for this reaction is the rate constant times the concentration of the organohalide. So it's the same as SN1. That also tells us that the concentration and strength of the base has no effect on the reaction rate. Again, because this is like SN1, you're waiting for the leaving group to leave, and the base can be anything with a lone pair. Weak bases tend to favor E1 like SN1. And for the most part, weak bases tend to be the same species as the weak nucleophiles. So things like water, alcohols, amines. We're looking for something that has a lone pair. Also, like SN1, the base often is the solvent. And that solvent tends to be a polar protic solvent. That's what's best for E1 because, like SN1, you're forming the carbocation and the leaving group with a negative charge. And polar protic solvents stabilize both of these species. Let's look at one last thing in terms of the reaction for E1 and how it's comparing to SN1. So let's say we take this tertiary bromide in the presence of water. Here's the rate determining step where we lose the leaving group to get the carbocation. That's the slow step. Anything that happens after this is going to happen at a much faster rate than the slow step. So this can undergo an elimination, or it can undergo a substitution. If it undergoes substitution, we're going to end up with an OH where the carbocation is at. If we do elimination, we're going to eliminate to give the double bond right here. That'll be the most substituted double bond we can get. And we're going to look at the regioselectivity in just a bit. So the main thing that I want to point out here is because our rate determining step happens before either of these, when you do this type of reaction with an organohalide and a weak nucleophile or base, we're going to get a mixture of SN1 and E1 products. Let's look at a few features of E1 elimination. First, in terms of the organohalide, it's going to follow the same trend as SN1. You have a primary halide that's basically not going to undergo an E1 elimination. Secondary, of course, is much faster, and you can use secondary halides, and you can use tertiary halides. Next, let's look at the regioselectivity. Basically, that means we're trying to figure out which hydrogen should we use to eliminate. So for example, if we were to start with this organohalide here, and I'm going to use water, and I'm going to add something else here. I'm going to add heat. And a lot of times you'll see heat added with elimination reactions because what that does is it helps to favor elimination over substitution. When we're doing these E1 and SM1 reactions, always think through the mechanism. That way you're not going to mess anything up. So with this, I'm going to lose my leaving group and draw the carbocation. Immediately, when you see the carbocation, you should classify it, and I will say this is secondary, and then think about rearrangement. So let me draw my leaving group in as well. But in this case, if we look at the carbocation, well, if I rearrange it to here, it'll be primary. But I can do a hydride shift and rearrange it to the left to get a tertiary cation. And that's exactly what I'm going to do. So I added the hydride here. I'm not going to draw it in. And then I get a positive charge on the tertiary carbon now. So always think about rearrangement. Now that we have our most stable carbocation, we need to figure out which hydrogen do we eliminate. So let me redraw this carbocation down here. What you want to do is find all of the carbons next to that carbocation. So I have one here, here, and here. And if those have hydrogen, draw one in to think about. All right, we have one here. I'm going to label that as A. We have a hydrogen here. I'll label that as B. And hydrogen here, I'll label that as C. Now, hopefully you can get to the point where you don't have to draw the products. You can just look at it and predict it. But for now, let's draw the elimination product from each hydrogen. Here's our three potential products. If you eliminate between HA and the carbocation, you get the double bond here. If you eliminate between HB and the carbocation, you get the double bond right here. And then if you eliminate between HC and the carbocation, you're going to get the double bond right here. And on C, you could actually get both double bond isomers. So in this case, we have this methyl on the same side as this methyl. You could potentially get the other isomer where the methyl is up here as well. But what you really need to do to figure out which product is going to predominate is think about overall stability. Which one's the most stable? The one that has the most substituted double bond. So if you look at the double bonds you formed, here's tetra, here's the di-substituted, and C would be a tri-substituted. So of these, the tetra-substituted is the most stable. This is the major product. And if we want to draw the electron pushing for this, in the presence of our weak base, water, that will come over and react with HA. Those electrons will then come down to form the pi bond.